So welcome everybody to this virtual time series seminar. We have Adam Sykulski from Imperial College London as a speaker and Peter Craigmile as a kind guest panelist. So Adam is talking about the Debiasing Welch methods for spectral density estimation. Thank you very much for accepting our invitation, and the floor is yours, Adam.
Thank you, Alessandra, and thank you everybody for attending today. And yeah, the title of the talk is Debiasing Welch's Method for Spectral Density Estimation. This is joint work with Lachlan Astvalk, who's the lead author on this work, and Ed Cripps as well, and they are both at the University of Western Australia. So before I delve into to Welch's method, I wanted to have a part one to this talk, which will just be a quick visual crash course in spectral analysis for those of you who don't, it's not your preferred tool in time series. I know some people, you don't need to go spectral, some people just don't like it. And for some of us, we gain a lot of intuition, and for others, they don't. And I thought maybe I'll try and create a more level playing field, and at least for an hour, you'll indulge me and think in this spectral way of representation of a time series. And the basic idea can be visually illustrated like this. Imagine a time series which is just a sinusoid that's oscillating with time, but with some period or some frequency. In this case, so it's sine 0.1t. So our time series looks like it looks here on the left. Alessandra, give me a nod if people can see my mouse. Yeah, because I can see.
Yeah, we can.
So, yeah, great, thanks, thank you. So we've got a time series here on the left, length so 1000 in time, and we see a bunch of oscillations happening on the left. Now, the idea with the power spectral density, we see an estimate of this power spectral density on the right, where it has this peak at 0.1 that corresponds to the frequency of the sinusoid. And we see this sort of slight bulging here because we're estimating a density. So for those of you who don't know power spectral densities, just think of any density. When you estimate it, you might have some kind of kernel or something around what you want to be estimating, and that's what we see here. Theoretically, we would get a spike because this is a deterministic time series. But I want to show you the estimates here so you get a sense of what the estimates look like for noisier time series. And the idea is that, okay, this is just us showing something quite simple here, but if we add, staying in the deterministic world, a second sinusoid with a different frequency, but also this time with a different amplitude, I've given the sinusoid a slightly lower amplitude of 0.6, our time series looks like it does on the left. But on the right, we sort of managed to beautifully separate these two peaks. We have a peak at 0.1, a peak at 0.13, and the difference in the amplitudes corresponds to the difference in the amplitudes in the governing equation. So we can kind of reveal sinusoidal structures in time series through power spectral densities. And then if we add a third one at a much higher frequency with a lower amplitude, then we can see it's buried here. We can't really see it on the left anymore. We wouldn't know, looking at the left, that there are three sinusoids creating that time series, but on the right, we can see these three peaks and conclude that. And so this tool is used a lot in many applications for finding these sorts of oscillations. And we could keep going with this idea, but what if our time series process lives at all frequencies and is in some sense stochastic? Well, this is the field of spectral analysis. So now let's imagine something that is noisier. Well, the basic thing we could start with is a white noise process. So xt is just some epsilon t, where epsilon t, for example, comes from a normal distribution. So here we just have a classic white noise. I've plotted it in white over time. And here the power spectral density also just looks flat. And that's one of the reasons it's called white noise, because it has a flat spectrum, the electromagnetic spectrum of white color, in case you were curious. Now, that's quite a boring stochastic time series. We could look at things like an autoregressive process. So we have an AR1 here with a positive AR1 coefficient, our time series now a little smoother than before. And as a result, our power spectral density estimate now has more lower frequency components than higher frequency components to incorporate this increase in smoothness in the time series that's happened. And this is why we, in signal processing, we often call this a red process, because it's shifted now towards the lower frequencies or the longer wavelengths, lower wave numbers, and that corresponds to the color red in the electromagnetic spectrum. Conversely, we might have a process which is more jittery than a white noise process. We could have something that's kind of anti-persistent, anti-correlated. In this case, for example, a moving average 1 process with a negative MA1 parameter, and we get this kind of up and down high frequency motion, and then the power spectral density is now shifted up in the higher frequencies omega, and we get a blue process in contrast, right? So these were power spectral density estimates of something that theoretically can be represented here, our power spectral density, by this equation that we're effectively calculating our theoretical spectrum by taking some limit of imagining we see a forever. So our t goes to infinity, over this limit, inside these limits, going forwards and backwards, of the Fourier transform of our time series, and we're squaring it, but then we're dividing by time. And this is for those of you who are curious why it's called a power spectral density, right? Because this thing in the middle is essentially in units of variance or an energy. We're integrating, we're saying how energetic is our time series by squaring it, but dividing energy by time, we get power, right? So this idea of a power spectral density, we're saying how much power there is at different frequencies. So that's the theory. In practice, what I was showing you in all those plots were from observing some sample of a theoretical time series at intervals delta. So we only observe these n lengths time series. And the most classic estimator of the spectrum is what's called the periodogram, which now compare these two equations. Now we can't integrate, we sum over our length n time series. We take the absolute value and square like before. We divide by n, similar to dividing by t, and we have a normalizing delta. And now S hat is an estimator of S. But of course, this creates uncertainty, right? And there are two sources here. First of all, we would want to be able to not sum, but integrate over an infinite horizon. So we'd want this n to go to infinity and forwards and backwards, but also what's happening in between if the true xt is a continuous time signal. So this creates a lot of uncertainty, and there's no reason to think that S hat is going to be a good estimator of S unless we have very large n, but also even that might not fix the issue, right? And let's have a look. So let's go back and look at our AR1 process. So we had this slide earlier, and if I add that theoretical spectral density, which has an analytical form, then we can see the periodogram's doing a reasonable job. It's very noisy, because the truth, if we were to observe this forever, would eventually go to the green line. But even over a length 1000 sample, like we have on the left, on the right, there's a lot of jitteriness in the periodogram. It's extremely variable, but it's about the right level everywhere. But problems occur when we go to more complicated processes. Here's an AR4 process with a very, this is actually, it looks very, very specific to pick these values, but this is very well studied in the book by Percival and Walden. This AR4 process, the time series looks like this. So it's quite jittery and noisy, but stationary. And the power spectral density, the theoretical, looks like this green line, but the periodogram, our estimate of the power spectral density, looks like the white line. And you can see we're getting a significant source of bias occurring for half the frequencies in this spectrum. And this really isn't that satisfying, right? If in reality, we want to be estimating the green line, but we observe the white line. And if we were assume that to be correct, we could do all sorts of wrong next steps, whether you're trying to forecast, predict, or model. etc., if you were to use this biased estimate, which is also still quite variable. And this leads to the famous quote by Tukey, which is that more lives have been lost looking at the periodogram than by any other action involving time series. And I've just illustrated you one example of why, because you can make wrong conclusions because it's not corresponding to the correct theory. So this is well known. I'm not the first person to be talking about this. Peter knows it well and others know it well too. And the state of the art, there exist many, many methods for correcting this bias and reducing some of the variability of the periodogram. These include, for example, multi-tapering methods, Welch's method, lag windows, and these have existed for quite some time. You can read about them, and this is Percival and Walden's Spectral Analysis book on these sorts of pages, and you can see that you can correct this white curvy line, for example, with a multi-taper estimate to this red line with some confidence intervals, which is doing much better than before. But it's, as you can see, it's still has maybe some bias, but also nothing comes for free. By smoothing, we potentially also add correlation in our density, and we might lose some resolution as well if peaks get close together. So there are always trade-offs that are happening. And that was just really a quick crash course to set up part 2. But before I move on to part 2, I do welcome questions or clarification questions during. So please do come in if you have any. I didn't mean to stop sharing my screen. Yeah, I'm back now. So please do. I can't see people, so just unmute yourself at any point. Otherwise, I'll continue. Yeah. Okay. So now change of color. Sorry if that woke you up. Part 2 is now on the theme of this talk, which is debiasing spectral estimates. And I'm primarily going to focus on Welch's method, but we've actually also adapted the method to work on multi-tapers and lag windows as well in a follow-up paper, which I'll shortly talk about at the end. So just to give some motivating application that I'll illustrate, I'll come back to later in the slides, but I just wanted to show you some plots now to get us thinking. These are time series of ocean beach sea surface heights. So this is over a period of 4,000 seconds, so just over an hour, and it's measuring sea surface height using 2 different types of instruments, an acoustic sensor and a pressure sensor. And these are of interest because the pressure sensors are much cheaper to collect, but there are some issues with them. The acoustic ones are sort of more like the truth, but they're expensive to compute, and that sort of gives a real practical reason to explore the relationships between these 2 types of sensors. The 2 different sensors measuring the same thing. And actually, if we take their log periodogram, so that I mean take the periodogram and plot the y-axis on a log scale to estimate the power spectral density, then you can see that they are essentially measuring the same thing at low frequencies, but at high frequencies, there is some disagreement, which is to be expected. And I'm going to come back to that later, but now I just sort of wanted to plant the seed that some of these differences may be real, but some of these may be also caused by issues with the periodogram and with bias, which I'm going to talk about in this talk. So just to lay some formal notation to introduce a time series, we're going to observe a real valued stochastic process. In this, for this talk, I'm going to make t just be an integer corresponding to our observation, and we're going to assume a 0 mean and an observation interval of delta equals 1, just for simplicity, but without loss of generality. And if xt is second order stationary, we're going to define the autocovariance function as gamma tau, being the expectation of xt times xt plus tau. That's what we would classically do. And we can also specify a parametric form for gamma tau and fit by maximum likelihood and other methods if we wish. So with that notation in mind, the power spectral density describes the distribution of power, as I described earlier, into sinusoidal frequency components F that describe the signal. Now, if gamma is absolutely summable, then there exists a power spectral density F that actually forms a Fourier pair with gamma. So F can be simply written as the Fourier transform of gamma over this infinite sequence of lag. So we're still in a theoretical construction here. And then simultaneously, gamma can be recovered from F by an inverse Fourier transform. So there's this kind of two sides of the same coin comparing F and gamma. So if you're not used to power spectral densities, you can just think of it as something that describes gamma, which is our autocovariance function, which everyone in time series knows. So we may equivalently describe a time series in this setting when we have satisfied these properties by its ACF or PSD for short. So for example, if we have an autocovariance function that decays but oscillates, like a periodic type, then we can, periodic type covariance function, then we could Fourier transform to reveal the periodicity of that peak in frequency, and we can inverse Fourier transform back from a spectrum to its autocovariance. And in fact, one of the reasons why Fourier spectral densities are so popular is via Bochner's theorem and similar theory, that on the right, it's sufficient that our density is positive everywhere, and by inverse Fourier transforming, we guarantee a positive semi-definite covariance function just by specifying a positive density on the right. Whereas the converse, it can be quite difficult to always specify a positive semi-definite covariance function straight out the bat and verify that it's positive semi-definite. Sometimes we can do it, but sometimes we're not sure. But by looking at its spectrum and checking if it's positive, there's this kind of if and only if relationship. So there are mathematical as well as computational, as we shall see, advantages to looking at power spectral densities. So empirically estimating the PSD, I already showed you this, that the periodogram we can define as this discrete Fourier transform over the length of our signal squared, normalized by the length of the signal. And in fact, we can show this is equal to a Fourier transform of our sample autocovariance. But this is the biased sample autocovariance, right? The one that we would classically use when estimating autocovariances. So this will end up giving a positive, although biased estimate to F, because the expectation, as we know, of our biased autocorrelation function has this triangle kernel placed before the true autocorrelation, such that it's going to be biased for all non-zero lags, right? Because we sort of divide our sample autocorrelation by n everywhere rather than by n minus tau for the biased version. So we get this bias coming here. But because the periodogram is actually the Fourier transform of the biased sample autocorrelation, we can expect bias in I as well, just visually from this slide. So what this means is you have this bias translates to this sort of blurring of the periodogram. So seeing as the periodogram is defined from a biased estimate of the ACF, we can also suspect that IN is also biased. And we can see that in this plot here, where this is with something called a Matern process, where the true spectral density is in blue and our periodogram is in gold. And I'm going to come back to FB later, but with the red, this FB is going to be the expectation of the gold line. So we can think of it as the expected periodogram, which will differ from the true spectral density. So the problem with the periodogram is we have this bias, and it's also an inconsistent estimator. The variability in the periodogram doesn't disappear as our sample length goes to infinity. So a lot of people enforce consistency using Welch's method. So Welch's method is a method that partitions a time series into m overlapping blocks of length L, calculates the periodogram of each block, and averages. So like you see in this visual illustration, we basically partition into overlapping blocks. There's going to be m of them. They're each going to be individually length L, and you have an overlap, which you need to specify, which you fix. And then you calculate periodograms for each component and average at the end. And this creates consistency because we're reducing variability by averaging over a growing number of blocks, right? As our samples get bigger. So the expectation, so Welch's estimator this is it in an equation. It does this, as I showed you in this figure. It does this averaging over our blocks. Now the expectation of Welch's estimator is actually going to be the true spectral density, and this is the convolution operator convolved with some curly f, which I'm going to come back to later. So we can try and characterize the bias of Welch's method by quantifying it as a convolution, right? And if we look at Welch's, some examples now, Welch's estimate of the wave data for the pressure data I showed you earlier, before this was the periodogram, which was quite, and this is Welch's estimate, which now smooths it out nicely. But so you can see we can resolve the signal, but it's also elevated some kind of noise floor in the signal. Notice that it's shifted everything up here, which is quite interesting, because is this possibly an increased bias that we're observing that Welch's estimate has created with a smoothing operation? Well, for finite samples, to decrease our estimator variance, we require m to increase, right? So this is the number of blocks. But if we have a fixed length time series, that by extension requires us to decrease the length of each block. So we increase m, we decrease L. But the problem is that decreasing L leads to increased bias, because as we decrease our block lengths, then these are all periodograms. And periodograms can be very, very biased for short length time series. And we just average over them, but we're averaging over bias doesn't kill bias. Averaging over variance can kill variance. And what that means is under Welch's classical method, we can actually become increasingly certain in an estimate that is increasingly biased as we seek to smooth by increasing m. And this can be really, really problematic. So before I talk about how we might correct this bias, I need to take you on a little bit of a journey to introduce a parametric method for removing bias when doing parametric estimation, because Welch's method is a non-parametric method. So I'm first going to talk about smoothing and removing bias from parametric estimates before then showing you how we can do this non-parametrically. So how do we manage spectral bias? Well, in a parametric setting, to avoid expensive matrix inversions, we can fit some spectral density that is modeled with some parameter theta with something called the Whittle likelihood. And we can do this in order n log n operations by using the periodogram. This is the periodogram here, in omega. And this form here, LW, is an approximation to the true maximum likelihood using something called the Whittle likelihood. And it's very popular because of its computational efficiency. Here, we just need to do a Fourier transform to calculate this, which we can do using FFT commands and n log n, and we avoid expensive matrix inversions of the covariance matrix, which you would have to do to compute an exact maximum Gaussian likelihood. So this is one of the reasons why it's popular, and you can see a nice proof of this in Claudia Kirsch's 2019 paper. Now, it's well known that the Whittle likelihood can be quite biased because the bias in the periodogram translates to biased parameter estimates of theta, because here we have something here that I've shown you can be quite biased, right? So what people often do in practice is they try and correct the bias in what I would call the data. So there's ways we could remove this bias. We could use tapering. But as I show in some of my research, this comes at the cost of introducing a different type of bias in our estimates of theta. We could do pre-whitening, which removes biases by creating something that looks more like a white spectrum, which is flat, so it can't be biased from its estimation. But this doesn't always work, and it's hard to tune without actually knowing what your model is. It's kind of a circular problem, pre-whitening, if you don't know in advance how to do it. And of course, you could collect more data at a higher sampling rate to remove the uncertainty. So you can recover the density exactly. But this is, of course, isn't really possible in the first place, because usually we're dealing with fixed length samples. So the work I did prior to this paper that I'm presenting you today is a different approach at removing bias, is to actually match the model in the direction of the bias data. So in the Whittle likelihood, we're sort of matching the periodogram to the spectral density, two quantities which one can be biased from the other. But because we have a model for theta, we can try and encode this bias into the model and then fit it to the periodogram. So we're going to call F tilde the biased spectral density. I'm going to bias the model in the direction of the data. And we need to incorporate these two effects of blurring and aliasing. So blurring I showed you earlier, which was this convolution effect that we convolve with something that is creating departures from what we expect to see and what we do see. And there's also an aliasing effect, this uncertainty of what's happening between our samples. And you could try correct for these things numerically by approximating this infinite summation, approximating this convolution, but these things are very numerically expensive to do. We have to approximate convolutions, we have to approximate an infinite sum here, but it turns out there's a trick. So I'm going to skip over, no, I don't need to, I'm sorry. So on this slide here, we can calculate this F tilde via a Fourier transform. So it turns out, and I'm going to gloss over the details, that because we have a model of the autocovariance, we can actually compute F tilde, which is going to be our biased spectral density, by taking a Fourier transform, but in a very specific way. We saw this triangle kernel earlier, the effect of the bias in the autocovariance with this kernel, and also rather than taking an integral here, we truncate the summation over the length of our data. So even though we know this functionally everywhere, we just sample it at the values we've sampled our time series. So this truncation multiplied by this kernel simultaneously accounts for the effects of aliasing and for the effects of blurring, because aliasing is accounted for by summing rather than integrating, and blurring is accounted for by taking this triangle kernel to correct for the effect of the blurring. And with a simple FFT, we can compute F tilde. And our argument is the debiased Whittle likelihood is basically, we still perform an FFT of our data to compute a periodogram, but then we also compute an extra FFT here, a second FFT to correct the model F tilde here and here in the direction of the data. And we found in simulations and theoretically, this leads to much improved performance of our resulting estimates of theta that we can correct for the bias that was present otherwise. And that's an older Biometrica paper here that I'll give the reference again at the end. Now, how can we use this to debias Welch's estimate? Well, what we're going to do is we're going to think about, instead of having a model, we're not going to know a model, but we could think of a Riemann approximation as a model. So think about a periodogram as a Riemann approximation to the true biased power spectral density, represented like this. So we have some periodogram in the background, which has some expectation, and we're going to Riemann approximate it, right, with just these blocks. And of course, as we increase the resolution of the bases, we can converge on the true integral. And then then as we increase everything, we converge eventually on the true biased power spectral density, right? So just increasing everything infinitely, we can eventually converge where we want to. Now, so what we can do from that is can construct a non-parametric model of our spectral density, just with a simple rectangular basis. So our F omega is just going to be a sum over bases B. Of course, we need to estimate these A's, right? And we're going to solve similar. I'm sorry, there's a row. I don't know what happened there. Delete that. We're going to solve similar to the parametric case. As before, that we have a model, right? And we can fit this model to our periodogram. But the point is that we know there's bias. So how do we remove the bias? Well, we're going to do some debiased semi-parametric inference here. So the corresponding ACF to each of these bases, so we have some rectangular basis B, well, we can actually have a sort of deterministic ACF corresponding to this basis. So we Fourier transform this basis here, and we get a rho tau, which is kind of an autocorrelation of our basis, which, because this is a rectangle, the Fourier transform of a rectangle, we can actually show very nicely, reference below, that we get a sinc kernel here on the right. So we can find this corresponding basis to our rectangular basis function once we take an autocorrelation. And because we have an autocorrelation, that's what we needed before to debias Whittle's likelihood. We can plug it into the same equation I showed you earlier, multiplied again by this triangle kernel over a finite sum, Fourier transform, do the correction, and we can tell you what the biased basis is. So this is, again, biasing the model in the direction of the data, taking a B tilde to incorporate the bias in the data. So we're going to effectively replace B by B tilde with a Fourier transform, right? So visually what this looks like is we have some bases B, and we're going to bias them by effectively blurring them out. So we're going to say in reality, we observe a blurring of these bases through the truncation of our data. So this is like a convolution of the true bases with this convoluting kernel, right? And then we can construct this model for our biased spectrum to be the sum of the same AIs as before, but multiplied by B tilde rather than B, right? So we have, this is our biased model that we can use. So the problem is that we are required to fit a large number of bases to the data that we, and we want to compute this, right? And we've established this as non-Gaussian. So how do we do this? Well, once we've established some strong mixing, we can appeal to the central limit theorem here and treat the data as Gaussian for a big enough M. Where this was, I apologize, this was earlier capital M for the number of blocks, right? So what we want to do, because it's impractical to fit all of these bases using Whittle's likelihood, there's too many parameters to estimate, but under central limit theorem, we can feasibly do this using a reweighted least squares argument here. So here we've got our original Welch's estimator, and we've got some parameters we wish to estimate by fitting to these biased bases. So we're going to take the square difference, but we need to reweight somehow. But the problem is that we need to reweight by the variance of Welch's estimator. But the problem is that that's model dependent. It's dependent on the spectrum, the very thing we're trying to recover. So there's a circular problem here. We don't know how to reweight our least squares because we don't know what this is. So here we can appeal to some theory and we can appeal to some asymptotic. I'm sorry, something's gone corrupted here, but theorem 2 will be sufficient for now, which is that basically what we can show is that we're trying to get the variance of Welch's estimate. But this theorem here allows us to show that we have, under fourth order stationary processes, so we can go beyond Gaussianity, with, as long as things are kind of finite and absolutely convergent in the cumulative function, look at segments of these periodograms, and even if we incorporate tapering, we have these two very useful results. That the first one is under Gaussianity, when the fourth order cumulative function is 0, and otherwise we have these asymptotic statements that relate the variance of a Welch type estimator to the actual square observed Welch estimator that you have. So the variance is kind of proportional to the square of the Welch estimator itself, as long as m, your number of segments, and l, the length of your segments, are increasing asymptotically. So you shouldn't fix either. As your time series grows, you should allow both to increase. And you can see there's an argument for kind of an optimal rate here of growing m with 2/3 of n and l with 1/3 of n that emerges here. I don't know what's gone wrong with my slides, but it looks like I can fix it just by moving on. Something's gone wrong in compiling this, I apologize. So basically, I'm just giving you the same result here again, that what we can do, just follow me on the bottom here, is this is what our original reweighted least squares, under this theory that we've established that things asymptotically are good, we can replace variance of I bar L with raised to the power of -1 with I bar L raised to the power of -2. And now we have an analytical solution. I'm sorry if I lost you there, the slides went a bit wrong, but basically we can arrive at a least squares approximate solution to our parameters of our non-parametric model, as I'm showing here. So this is really quick to compute now, right? This is just analytical. This is like instant. So it's a really fast method that we can do. And then, so just a summary of the mathematical findings, we require a large number of bases, and so numerical optimization is not feasible. But due to the averaging inside of Welch's estimator, our central limit theorem implies that a weighted least squares fit is appropriate, conditioned on knowing the weights. An analytical solution is available, but we show that the weights are asymptotically proportional to Welch's estimator itself. So we have a good estimate of the weights with bounded rates of convergence. And we can prove mathematically motivated guidance for optimal choices of L and M based on those rates of convergence. And the debiased Welch estimator remains an order n log L estimator, because we just have to take Fourier transforms of length L segments. So it's all still super fast. Now, just to give some plots. So this was the wave data we looked at earlier, the pressure measurements in the time series. The periodogram looked like this, where we weren't sure what was going on here in the tail. And this was corresponding to the time series you see here, where we have the pressure in red and the acoustic in blue. Now, here are our two spectra again. On the left, the acoustic, on the right, the pressure measurement. And we want to try relate these two and compute both Welch's and debiased Welch's estimated to compare them. So the relationship between the two has an additional complexity because the pressure signal is actually attenuated, but in a deterministic sense with depth Z here that we can correct for. And what that means, just to explain that, is on the left, we have an acoustic measurement periodogram. On the right, we have a pressure measurement, but some of the difference is explained by this red line, because the gold line should, in theory, be the left-hand plot, which I've given in grayscale here, multiplied, attenuated by this red line here. So at low frequencies, we expect them to be the same, but at high frequencies, we're expecting this to be attenuated so that it's suppressed at these high frequencies. So some of this suppression that we're seeing here is physically expected from the instruments. But we know the function, so we can actually reverse this attenuation if we like. Now let's look at the estimates of the pressure sensor. So Welch's estimate, recall that this kind of flattening here, but when we debias Welch's estimate, we find actually they look very, very similar at low frequencies, but at high frequencies, we seem to be able to go lower down in power and higher up in frequency before we reach perhaps a new noise floor that is a couple of order of magnitudes lower than before. So we seem to be able to go a little bit further than this sort of noise floor that we're observing here. So maybe this was real, maybe it wasn't, but our method suggests maybe this, what's going on here, is an artifact of the estimator rather than the true process. Because when we debias, we can go a bit further in the spectrum. And why is that useful? Well, if we reverse that attenuation and compare to the acoustic sensor, the more expensive data, then we see with Welch's estimate, when we reverse the attenuation, we actually go all wrong here in the 0.2 to 0.3 bin, where suddenly this bias is translating to an inflation in energy that shouldn't be there in power at these frequencies. But with the debiased Welch, we could go further all the way to 0.3 hertz and map these two together. Beyond that, things go wrong, but we've sort of recovered an extra 20% of the signal in terms of frequency content by going from 0.2 to 0.3 hertz, where we can map the two. And this is practical implementations because, like I told you, the pressure sensors are cheaper. So we can figure out what the truth is from the acoustic sensors up to a higher frequency, which has some advantages to the oceanographers. So just to round up with some simulations from Percival and Warden's AR4 model, if we compare what we're going to call debiased Welch by dWelch and p-Welch by the original Welch method, then what we find, the dashed lines are all going to be the original Welch, dWelch is our method, then we can bias reduce, because the bias before, when we increase the number of segments, remained constant with Welch's method. That was the problem with Welch's method, is we're killing variance, but we're not removing bias. But here we show we can send the bias towards zero, right? We can remove it. And when it came to root mean square error, then actually we found when it comes on the right part to standard deviation, we found all methods performed about the same. The root n optimal convergence rate we'd expect under kind of central limit theorem arguments of variance reduction. So we've maintained the variance reduction, but removed a lot of the bias. And when combined to compute root mean square error in the middle, we found that we could outperform the classical Welch method, as you see here, and that happened for all possible choices of m. If we set m to be really small, then yes, we could run into situations where we do worse for short time series than the original Welch, but in almost all instances, we found improvements. Just as a further selection of simulation results, if we fix L, which is the length of the segments, and increase M, then just the computational time, there is an increase from the second Fourier transform. We found around 0.14 seconds. So we just think this extra computation is worth it, and what are already fast methods to debias. We have this now, we're increasing M with fixed L. We found similar root mean square error convergence at the rate we'd expect. And this is an interesting plot that if we fix N and look at the trade-off between L and M, so this is the number of segments M and the length L, then Welch's method in the dashed line has this classical U-shaped relationship where variance dominates with high L and low M, and bias dominates as we make our block lengths low and our number of blocks high. And there's this classical bias variance trade-off that we need to optimize. But what we found was by reducing the bias, what that means is we can kill the error on the left-hand side. It's still there on the right-hand side. But what that allows us to do, you see, is optimally pick higher values of M, because we can bias correct for low values of L. Eventually, this will break if I go below 0.25. But in this kind of crucial region here, we found this is where our improvements lie, that effectively we can increase the amount of segments in Welch's method and inherently reduce the amount of variance. Okay, and then something's gone wrong for my final slide. Something's gone wrong here, but if I scroll down and make this bigger, I apologize for this. then this is just to round up with some software and references. So for parametric estimation, we have a debiased spatial Whittle likelihood Python package. And then for the non-parametric estimation I showed you today, we have both an R and Python package called Specky, which is available here under this GitHub account. And then what I presented to you today, debiasing Welch's method, is available in Biometrica from last year, but we also have a paper under review on arXiv, which is a bias correction of all quadratic spectral estimators, including multi-tapers and lag windows, where we've extended our ideas to other spectral density estimators beyond Welch's method. And the original Whittle likelihood correction papers for time and space in the final two references. So I apologize for whatever went wrong with the corruption of my slides there, but I think it still worked. And thank you very much for your time.
Thank you very much, Adam. Let me stop the recording now.